Hello and welcome back. Today we're going to have a look at two power supplies. Both are from the brand Jetfon. They have a lot of power. One can go up to 55 amps and this one can go up to 60 amps. So both can deliver lots and lots of power. And we're going to have a closer look. I will open them also. And then we're going to find out which one is for what purpose the best to use. Closer look at the front. We can already see a few differences. This one has the analog readout. This one has the digital readout. Both have the cigarette lighter plug for your car devices that you can plug in, which is very convenient. Both have a setting for 13.8 fixed or variable from 5 to 15, and this one I think is 8 to 15. Well, in this one it's all the way in the back. Well, another difference is here you have also some lower power connections in the front, but the big connectors are in the back, and here we have the big connectors in the front. Also another difference is that the power is here in the front while it is here in the back. Then we have a look at some of the extras that one has against the other, and that is here we have the USB. It's fixed 5 volts, 2 amps. This is great to charge. And here you can also set the voltage in the front. We can do that here also. And an extra what this one have is that you can set the constant current, so you can limit the current setting here. Well, in this one that option is not available. This one has a little bit more of a classic look, but a good thing is that the power button is in the front. This one looks more modern if we switch it on, but the power button is in the back, which is very inconvenient in my opinion. And the ventilator is immediately running. This one is silent and this one immediately makes a lot of noise. Another extra that this one has is a noise offset, and you find this mostly on the power supplies that are designed for ham radio. Both these power supplies are switch mode, and that means that even though they are made with a lot of care, trying not to make any distortion, you could still have a little bit. So if you're using the power supply for ham radio, you probably want a power supply with this noise offset. So if you are a little bit unlucky and you are listening to a certain station that is just on harmonics of one of these switching frequencies, then you can just change it a little bit. It will not change the voltage, but it can just move enough that the harmonic of the distortion just goes away and you don't hear it. And this one doesn't have that option. When we have a look at this one, it looks nice and compact. The front is plastic, but the top is metal, the bottom is metal, and we have here the huge ventilator that we can hear, and the power button is on the back. And then this one, the PC55, it doesn't have the big power terminals in the front, but it has it in the back. And that is okay because it needs to be big, and you probably use one of those power strips to distribute to more of your transmitters. Also the switch is in the back here for the 13.8 volts or the adjustable, because if you use it for ham you probably will just keep it to the 13.8 and that is it. So before we open it, a little sum up. Power button in the front, big terminals in the back. Also the switch between variable or constant 13.8 volt is in the back, so that's difficult to reach when it is built in your stack. For this one it's exactly the other way around. The power button is in the back and the big connectors are in the front. Switching it over from fixed voltage to variable voltage, that is nicely done in the front, and it has an extra USB connector, but it doesn't have the noise offset function. And a big turn off is of course the the noise that it produces when you switch it on. They sell it in the leaflet I saw, they sell it as a constant cooling power supply, which actually means it's making noise all the time, so they know how to sell this. But we can of course change this with PWM PCB. I will do that, and also I have already another terminal here because that is broken. Yeah, let's have a look inside. Although this one is digital meters or a digital readout with the 7 segments LEDs, somehow this looks a bit less delicate. It is all, yes, it has a lot of cooling, we have a lot of heat sinks here, but somehow the technology looks older. Also, when we look at how these meters are, yeah, I don't know, somehow it feels a lot older than when we look at this one. This one here, not too many components, but it looks proper. And the whole bottom plate is the heat sink, and the ventilator is just switched on when it is really necessary, and that is here with this just on-off switch. What I do like of this power supply with the analog meters is here you can see really the separation of the high and the low power. What they did in the PCB, making these air bridges everywhere, also here. So it just seems a lot more solid somehow. And when we look here at the 12 volts, the low voltage area, they have all nice extra caps, and the wires look really thick, which is a good thing. The connectors also here on the PCB looks to be all properly done. It just looks a bit newer somehow. We have a look again at the one with the digital readout, and this one's supposed to go to 60 amp while the other is only 55. But when we look here at the cable thickness that we have here that goes to the terminals, it is actually less thick than the 51. So somehow I get the feeling, even though this one can go up to 60 amp and this one 55, that this one is somehow older, and it has a digital readout, but still it is older. The way it is built, also the front is plastic and the back is plastic, while here only the front is plastic but the rest is all metal. Also, when you look how it's screwed together, this one has only 4. It has 2 little strips here to make it at least a little bit fixed, and this one just used a lot more screws. This one had 10 screws, this one has 4 screws. It just seemed also to be built better. So what we have seen so far, I would say that if you want for ham radio, I think you go for this one because of the noise offset and the cooling that is only switched on when it is needed. And I think they can do this with this simple temperature sensor, because when you use it with ham radio, most of the time you receive and then you have a short time that you transmit. So during receive maybe you have a few amps, and then when you start transmitting it can go up to 25 plus, and then it has time again when you receive to cool down a little bit. And yeah, the noise offset of course is the main thing. Well, this one, although it looks newer because of the digital readout, it looks to be built older, but maybe it's also made for more continuous power all the time, and that's why it's also cooling all the time. And a nice thing is when you use it for a hobby, you can just limit the current also with this button here, and that is here, that is not possible. You can only set voltage. So if you are watching this video because you like to make a decision to buy this one or this one, because the pricing is about the same, and you maybe think because of the digital readout this one is a lot more modern, I don't think so. This one looks, the technology looks a lot better. It is silent, and a big turn off with this one is the noise and the switch in the back. So I would say ham radio or heavy duty hobby power supply. So let's have a look at this one, the 60 amp. The other one is good. I will just leave it as it is. It was new. But here, of course, we need to do something with the terminals. This one I bought secondhand, that's why it's missing. And I want to do something about the ventilator, of course. And maybe I move the power switch to the front. Then I can just get rid of this C-car plug thing. And then I can just, because the switch is now on this side, so I can just, if I can isolate the cable a little bit, I can just move it here to the side and then connect it here and have a switch here or like this. That would be much more convenient. The front is sort of a sticker, and here the switch is not fully correct in the sticker. So I want to put that also correct. All the USB is sort of okay. I don't think I can do too much here. Then try to glue it, but I don't worry too much about that. I noticed that the readout was a bit high. It should be 13.8. I didn't measure the voltage itself, but we can probably adjust that. And this one was missing. I found on the AliExpress. I found exactly the same, hopefully exactly the same. And so hopefully I don't need to replace them completely, but I can just, yes, I think that is exactly the same. Perfect. Okay, so that is good. Now let's have a look at the voltage and the current, if it is correct or not. Okay, I have the cyclant in the back there. Let's switch this on. It says 13.9, but how much do we have really? We have 14.1. That is too much. So is it the meter is not correct and the output is not correct? So let's have a look at that. There is of course a difference between adjusting the meter or adjusting the output. Now I found a lot of pots. So there are pots here on the back of the meter. So right here. So this will probably be the meter display. And here we have cables, and that one goes to the shunt right here. And I see here a white and a red cable. So this could be the current, and then because this is farther away, this is probably just the voltage, but this is to display. And then we have on the main board, we have a few pots. Let's see if we can, we have a pot here, and we have a pot here, and we have a pot here. One is probably the current limit, and I think that is this one, or this is the preset for the current limit. Then this is the full current limit, because if I check the wires, this goes to the pot here in the front for the current limit, and the switch that says adjustable or fixed, that goes to this one. So this is probably the 13.8 preset. And one of these are the current limits. So the current limits I probably don't touch. I will set the 13.8 right here, and then we adjust the front here. Well, that is mostly guesswork, but I think, well, first the easy stuff. Let's just see if we can push this switch out, and then maybe we can refit it and then correctly with the sticker. Yeah, there it goes. Makes a little bit of an unfriendly sound, but okay, that looks better. So my guess was that when we switch over from this one to this one, this would be the 13.8. Yeah, it seems to be. Okay, then the voltage, then we need to look at the front. Okay, then I think it was this one on the front. I'm not sure if the heat sinks are isolated or not, so I need to be a little bit careful. I'm actually a bit scared. So I will do it like this, because this Chinese power supply, I don't know if the heat sinks are just on the mains or not. Okay, I think. Yeah, that's indeed correct. So this should be go to. Okay, so the voltage readout is now perfect. 15.4, it's the max. This is 15.4. We go a little bit down. 7.4, 7.6, 7.8, 15.4 or 13.8, 13.8, 13.8. That is good. Now I want to have a look at the current. So I'll just be switching this on, setting it to 10 amp. 10 amps. But the power supply is still very noisy. Let me just start by 1 amp, and it doesn't display at all. 2 amp, 3 amp, 4 amp, 5 amps, and it doesn't say 5, it says 3.1. So let me go up a bit. Let me go to 40 amps and adjust it to 40. Now it says 38. Okay. Let's see if it will blow up or not, because I'm putting some reasonable power. And I think this is from the shunt. I will not touch the main board, because on the main board, that is my electronic load starting to make noise now. For getting the current right is a little bit more difficult than I expected. I just cannot get it right. If I set it to 10 amps, it says it's 9.7, so I said okay. Now I have it on 30 amps and now it says too much. So somehow the linearity is not correct, but I cannot find where I can adjust that. Another thing I like to see now is we see a lot of heat sinks, and I like to see which one is the most hot, because that is the one I'm going to use the PWM module on, because I only have one temperature sensor. So that means I just leave it running a while on this 32 amps, 30 amps. And yeah, the hottest I'm going to pick. I have the Infrared P2 right here. And look at that, my cables, because they are running 30 amps. The cables are warm, the terminals are warm. The most heat seems to come from the 24, 24, 24, 24. This heat sink, yeah, 35. And here the current shunt. The current shunt is the most hot. So we found a few hot spots. This one, I think that's the rectifier is connected to that. We have this, I don't know, it's NTC, and we have these ones who are actually very cool, so in that sense it doesn't need cooling. And we had this here, the current shunt, but the current shunt is just open, so I don't want to do that. But this one was around 60 degrees. But I found that this resistor here is also 60 degrees. I think it's safer, it's also nicely isolated, and I have the ventilator here anyway, so I can do my PWM module here, and I just sense this resistor. Yes, and it's still hot. Yeah, it's a lot hotter. So before I start to play with the PWM module, I just let it cool properly because the resistor was still around 50 Celsius. So I will put the cover on just to make sure that all the proper components get cooled. I think it's supposed to be like this. No, like this. Air gets in here, goes through all the heat sinks, and here it just goes this. Yeah. I have a few modules. I have one here that is also PWM, but it is fixed with a small ventilator. And I'm not sure if the board can do that bigger ventilator. So I need something else. I have here also a module, but this is just thermostatic. It's the W1209, very famous thermostatic switch, but then it is just on and off. So I really want a PWM thingy, and I think yes, these are 12 volts. Yeah, it is it. I think, yeah, 12 volt, 0.8 amps should be enough, with the temperature sensor that I can connect to that resistor. And well, here I can connect the fan and everything. Okay, let's see. So we have the module right here. It's very simple. We have the fan here, the NTC there, and the power in is there, and it is made for 12 volt. I haven't checked if the fan is 12 volts, but I just assume it is. So the NTC we just get, and let me just pull for a little bit more length. It goes here, and then I can just mount it somewhere on this resistor, and I need 12 volts in. I can take that directly from there. So everything comes with this little module. I'm not going to worry about the programming yet, but with this key here you can program which temperature it needs to do what. First I'm going to see if it even works. So the plus is on this side, the minus on the other side, and the sense we are not going to use. Okay, so this should be that, and then we have the fan, and we have the black one in the bottom, so that will be like this. Can we force this a bit that it will fit? Yes, we can. Okay. Well, let's see what it does. Okay, the fan goes. It is not in full speed. Let me get the solder iron to heat a little bit the sensor. It is running already, but I totally forgot about the fact that the resistor was already hot. So when now it's going faster. Here it goes. Full speed. Okay, it turns out that resistor I found is always getting hot, no matter if there is a load or there is no load. So still the best where I can measure then the temperature is on the current shunt itself, or at least in the proximity of that sensor. And I know you can program this device, the PWM module. So I will now look on my computer to see, because you can set somehow the minimum speed of the fan and the maximum, and how fast it needs to scale up. So I want to have a look at that. Here is the connection. Sense is optional. 12 volts in, fan out, fan plus. I did that. Then how to program, and you can set the minimum speed and the maximum speed, and when it needs to go up and how fast. So step 1, set the minimum fan speed, unplug the temp sensor, power on, see the light to, click to increase, double click to decrease. So minimum speed is without the sensor, so we do that, switch it on, the fan will go, and if I click once, it is going faster, yeah, and double click, slower, yeah, I can hear it go lower. Okay, now we need to do the temperature that it needs to start increasing, and I will just see what is the default setting. So maybe we say, okay, when it's above 40 degrees, then it needs to start to accelerate, and then when it is 20 degrees above that, so 60, then it should go to full power. So then I want this setting and this setting. So with the temperature sensor connected, I need to push and hold. There is only one button. Then it starts to flash. And what does it say then? It starts flashing at 1. So that means at 30 degrees it starts. This is 35. And this is 40. But I go back. Then, well, it's the current shunt. So let's say 35 degrees. Long push. Now it's blinking fast, and now it's the other setting. So 5 degrees above that, it starts to accelerate like crazy. Now, then we say do that 10 degrees. Press and hold to save. So I need to fit it just here close by to the shunt there. And I have some thermal, well, it's not paste, but it is some thermal stuff that I will put in between, so I don't get an electric short circuit and it still makes contact. So I will try to do it like this, and then try to fit it in between. I'm not sure if it's poisonous, but I will clean my hands after. Okay, a little test run. It is now on low speed, getting the electronic load. Yes, the ventilator is now at full speed, and the shunt is now around 40 degrees. The rectifier is 35, and the shunt is now 40, and it is now full power. 25, 25, 25, 25, and that resistor is always around 40 degrees. Maybe I can put a heatsink on that resistor. but the shunt is now the hottest, so that's a perfect point to put it. Cool. So the shunt is cooled down and the sound is completely off again, so that works good. So that fan noise has improved a lot, and it will actually step up when it needs to. So I'm very satisfied with that. The power switch I will do another time, because in the end it looks great as it is. Thank you for watching, and I hope to see you next time.